Hello, Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to all of you. Okay, we now in the first topic of the subject CES513. The title is Solution of Nonlinear Equations. So basically we have two methods in this topic, which is the first one is Bisection Method and the second one is Newton-Raphson Method. Okay. For this video, I will discuss about the first method in the first chapter, which is the solution of nonlinear equation using bisection method. Now, for the learning outcomes, at the end of this topic, you should be able to analyze, identify, formulate, and solve related civil engineering problems using the bisection method, and you should be able to use the bisection method to solve civil engineering problems according to the required absolute relative error or true error. Alright, we start with a motivation as the background of this topic. As you can see here, we have a quadratic formula which is fx equal to ax squared plus bx plus c equal to 0. So the values calculated with this equation is actually the roots of the top equation, the fx function. So what is roots? Roots is actually values of x that make quadratic equation equal to 0. That's why sometimes the x is also called as the zeros of the equation. Although the quadratic formula here looks simple, but there are many other functions for which the root cannot be determined by using this equation. So for these cases, the use of numerical method could provide the answer that we need. Okay, so that means roots can be determined either by analytical method or numerical method. Before the era of digital computers, there were several ways to solve for roots of equations. So these methods are actually the non-computer methods for determining roots. The first one is direct method. As the example on the previous slide, that the roots can be solved directly using the quadratic formula or analytically. But there are many functions that cannot be solved analytically. So the other alternative for this kind of function is an approximate solution technique. The second one is the graphical method, where we can obtain an approximate solution by plotting a graph of a function and determine where it crosses the x-axis. So this point here is represent the x values for which the function equal to 0. So that is called s-root. These graphical methods are useful to obtaining rough estimates of roots, but they are limited because of their lack of precision. And the third one is trial and error method. This technique consists of guessing a value of x or the root of the function and evaluating whether fx is 0. So this process will be repeated until a guess is obtained that results in an fx that is very close to 0. These unsystematic methods are obviously inefficient and inadequate for the requirement of engineering practice because we need a very precise answer. So thus, the techniques that will be described later in this video represent an alternative that are also approximate but employ systematic strategies to find the equation root. The combination of these systematic methods and the use of computers will make the solution for root finding problems simple and efficient. Okay, let us take a look at example 1 for graphical method. A parachutist's velocity can be determined using the equation of fx here. Okay, use the graphical approach to determine the drag coefficient C needed for a parachutist of mass m equal to 68.1 kilogram to have a velocity of v equal to 40 meter per second after free falling for time t equal to 10 seconds. Note that the acceleration due to gravity is g equal to 9.81 meter per second square. So we need to find the drag coefficient C in this example. Okay, for the solution, substitute all the parameters given in the problem into this equation, and then determine the points for C and FC. Okay, a series of points of C and FC, and then plot these points into the graph. So the resulting curve crosses C axis between 12 and 16. So this is the range where the root located. By visual inspection, the plot provides a rough estimate of the root of 14.75. Okay, and the validity of the graphical estimate can be checked by substitute the value of 14.75 into this equation. Okay, so we can see that it is satisfactory because the answer is near to 0. Alright, so now we look at a tree of on how to determine roots of equations. So basically there are two methods for determining a root. Okay, the first one is bracketing method and the second one is open method. Okay, so under the bracketing method we have bisection method, which is the topic that we are discussed now, and then we also have graphical method from the previous example 1, and then we have false position and incremental search. Okay, for the second method, which is open method, we have fixed point iteration method, and then we have Newton-Raphson method that will be covered in topic 1.2. We have secant method, branch method, multiple roots, and non-linear systems. So basically for this subject, we will only cover two methods of finding roots for equations. The first one is from the bracketing method, which is bisection method, and the second one is from the open method, which is called Newton-Raphson method. The bisection method is actually one of the bracketing methods for finding roots of a function. Okay, it starts with guesses that bracket the root and then systematically reduce the width of the bracket. So error formulations are developed to help you to determine how much computational effort is required to estimate the root to a pre-specified level. The bisection method, which is sometimes also called as binary chopping, interval halving, or Bolzano's method, is one type of incremental search method in which the interval is always divided into half. Okay, if a function change sign over an interval, the function value at the midpoint is evaluated. So the location of the roots is then determined as lying at the midpoint of the sub-interval. And then the process is repeated to obtain the refined estimates. The method is based on the three theorems. So an equation fx equal to 0 where fx is a real continuous function, has at least one root, okay, in between lower bound and upper bound, xl and xu, if function of lower bound multiplied by function of upper bound lesser than 0. This can be seen from figure 2 in the next slide. And then B, there may or may not be any root between lower bound and upper bound, or xl and xu, if the function of lower bound multiplied by the function of upper bound greater than 0. Okay, so this can be seen from figure 3 and figure 4 in the next slide. And then C, there may be more than one root between lower bound and upper bound if the function of lower bound multiplied by function of upper bound lesser than 0. This is the case of figure 5. Okay, let us look at these figures. For figure 2, at least one root exists between the 2 points of lower bound and upper bound. If the function is real, continuous, and changes sign. Changes sign means from negative here to positive. Okay, for figure 3, if the function fx does not change sign between the 2 points, you can see here lower bound is positive and upper bound is also positive. That means the sign is not changed. Roots of the equations may still be exist. Okay, if you can see, we may have 2 roots here between the 2 points. Okay, and then for figure 4, if the function does not change sign between the 2 points, there may not be any roots for the equation fx between the 2 points. So, for example, here we have lower bound and upper bound, positive, positive, and there is no roots in between these 2 bounds. And then for the other case, we have negative lower bound and upper bound, and there is also no roots between these 2 bounds. Okay, and the last one is figure 5. If the function fx change sign between the 2 points, okay, we have lower bound, positive, and negative upper bound, more than one root for the equation may exist between the 2 points. So we have 1, 2, 3 roots. Okay. Okay, now this the step of bisection method. Step 1, choose lower bound and upper bound, xl and xu guesses, for the root such that the function changes sign over the interval. Okay, this can be checked by ensuring that function of lower bound multiplied by function of upper bound is lesser than 0 or negative. Okay. And then step 2, an estimate of the root xr is determined by the equation of xr equal to xl plus xu divided by 2. And then number 3, make the following evaluations to determine in which subinterval the root lies. Okay, A, if the function of lower bound and the function of root lesser than 0, that means it lies in the lower subinterval. Okay, therefore, set upper bound equal to the estimated root and return to step 2. So you need to return back to step 2. Okay, B, if the function of lower bound multiplied by function of the estimated root greater than 0 or positive, the root lies in the upper subinterval. Therefore, set lower bound equal to the estimated root and return to step 2 again. And the last one, C, if function of lower bound multiplied by function of the estimated root equal to 0, then the root is equal to the estimated root lah, XR, and then you can terminate the computation. Now we look at example 2 for the bisection method. Use bisection method to solve the same problem approach graphically in example 1. So note here that the true value of the root is actually equal to 14.8011. Okay, the first step in bisection method is to guess two values of the unknown that give values for function x with different signs. Alright, so from figure here, we can see that the function change sign between 12 and 16. Okay, so 12, the function is still positive, and for 16, the function is already negative. So it's change sign. And then figure here shows the graphical depiction of the bisection method for this example. So for example, this one is actually for the first iteration where the lower bound is 12, okay, and the upper bound is 16, yeah, and the estimated root is equal to 14. And then the other one is for the second iteration where we have lower bound equal to 14 and upper bound equal to 16, and the estimated root is 15. While for the third iteration, we have lower bound 14 and upper bound 15, and the estimated root is equal to 14.5. So we will see this in detail after this. Okay, now we start with the first iteration where the lower bound is taken as 12 and upper bound taken as 16. And then the initial estimate of the root, XR, lies at the midpoint of the interval. So we can get the estimated root as equal to XL plus XU divided by 2. Okay, then we get 14. And then this estimate represents a 2% relative error, okay, epsilon t equal to true value minus approximation divided by true value times by 100%. So here we will get the true percent of relative error equal to 5.4%. Next, we compute the product for function lower bound and midpoint. So the function of lower bound, okay, by using x equal to 12, we substituting into the equation, we will get 6.114. And then the function of the estimated root, which is 14. So there is a f here. Okay, we will get the function for estimated root equal to 1.611. And then when we multiply the function of lower bound with the function of the estimated root, we will get 9.850, which is positive. So when the answer is positive, that means no sign change occurs between the lower bound and midpoint. Thus, the root must be located between 14 and 16. So it's like this. Okay, we have the lower bound of 12 and then the upper bound of 16. And then we have the estimated root of 14. Okay, so this one is lower bound, upper bound, and the root. So if we test the function of lower bound and multiply with the function of the estimated root, and then we get positive here, positive. That means there is no sign change occurs between the lower bound and the estimated root. So it means that there is no roots in between 12 and 14, and the root must be lies between 14 and 16. Okay. Okay, following the first iteration, the new interval created by redefining the lower bound as 14 and the upper bound as 16. So we have from the first iteration is 12 to 16, and then we have the estimated root for the first iteration is 14. And since we test the function of 12 and 14, the multiplication of function 12 and 14 is equal to positive. So that means the new interval that we need to consider is from 14 to 16, which is for the second iteration. 14 will be the lower bound and 16 will be the upper bound. Okay. Then we get the estimated root from this equation, 14 plus 16 divided by 2, which is 15. Okay, that is the estimated root. And then calculate the percent of relative error, true percent of relative error. Why we call it as true percent of relative error? Because we are using the true value of the the x. So we get the true percent of relative error for the second iteration is 1.3%. Now, as the first iteration, we calculate the product of function for lower bound and midpoint, or the estimated root. So here, the function of lower bound by using x equal to 14 is equal to 1.611, and then the function of the estimated root, okay, here, which is value of 15 for x, we get negative 0.384. And when we multiply the function of lower bound with the function of the estimated root, we will get negative 0.619. So we can see here there is sign change occurs between lower bound and midpoint. So that means the root must be located between 14 and 15. Okay, so I will show you graphically. So the lower bound is 14 and the upper bound is just now 16. Okay, and then we get the estimated root of 15. Okay, this one is the lower bound, 16 is upper bound, and 15 is the estimated root. Then when we test the product of function lower bound and estimated root, we get negative here. So that means the root is lies in between 14 and 15. Okay, thus the new interval is considered as 14 and 15. Okay, and then continue with the third iteration, where just now we find that lower bound is 14 and the upper bound is 15, and the estimated root will become 14.5, which is equal to 14 plus 15 divided by 2, we get 14.5. And the true percent relative error, as usual, the true value of x multiplied by the minus by the estimation and divided by the true value, multiplied by 100, we will get 2.0%. And the method can be repeated until the result is accurate enough to satisfy our need. Okay. Now, The steps in bisection method can be repeated until the result is accurate enough and a refined estimation of the root is obtained. But when to terminate is depending on the termination criteria and the error estimates. So the initial suggestion is to end the calculation when true error falls below some pre-specified level. So this strategy is flawed. Okay, flawed because the error estimates in the example were based on true root of the functions. So this would not be the case in the actual situation because there would be no point in using the method if we already know what is the true root. So usually we don't know what is the true root. That's why we need an estimated error that is not dependent on the actual root of the function, which we don't exactly know, and one is called as approximate percent relative error. Okay, so we can get this relative error equal to the new estimation minus with the old estimation divided by new estimation multiplied by 100%. Okay, so when the approximate relative error become less than the pre-specified criterion, okay, epsilon s, so that is when the computation need to be terminated. Okay, it is also convenient to relate these errors to the number of significant figures for the approximation. So the relationship can be seen from this equation where epsilon s, or the stopping criterion, equal to 0.5 times by 10 power of 2 minus n. So n here is actually the number of significant figures. Okay. So from there, it can be shown that if the following criterion is met, we can be assured that the result is correct to at least n significant figures of approximation. So now we will look at example 3 for the error estimation. Continue example 2 until the approximate error falls below a pre-specified stopping criterion of 0.5%. So given in the question, the pre-specified stopping criterion equal to 0.5%. So for the solution, remember that the results of the first two iterations for example 2 is 14 and 15. Okay, so the approximate relative error epsilon A will equal to new estimation minus old estimation divided by new estimation, then we'll get 6.667%. Recall that for the estimation root of 15, the true percent relative error is 1.3%. So we can see that the approximate relative error is greater than the true error. And if we check with the stopping criterion, epsilon s, the relative approximate error is still greater than the stopping criterion. Thus, you need to continue the computation. So from the table of the iteration results here, we can see that after 6 iterations, the approximate relative error finally falls below 0.5%. And so that the computation can be terminated. Okay, the irregular nature of true error, if you can see here the true error, because of the true root in bisection method, can lie anywhere within the bracketing interval. Okay, it's not stick in one location. So the true and approximate errors are far apart when the interval happens to be centered on the true root, and they are close when the true root falls at either end of the interval. Okay. So basically here, when we know the true value of the root, which is xt, then that is when we can calculate for the true error. But if the true root value is not given in the question, so we just have to calculate the approximate relative error. Okay, I think that's all for the topic of 1.1 bisection method. You can refer to the lecture notes for more examples, and I also give exercise in the lecture notes for topic 1, a question from previous final exam, so that you can do it on your own. Alright, thank you very much. See you again.